The next speaker is François Laudenbach, University of Lyon. And the title is Most Complexes for Manifolds with Non-Empty Boundary and Agency Structures, Applications to Linked Hardware.
Thank you again for this invitation. I should say that it is a great occasion for me because it is the first time I'm coming to Japan. Okay. So I discussed Morse theory on manifolds with non-empty boundary, but of course it applies also to Morse-Novikov theory. It is exactly the same thing. And I would like to start with the example which I have in mind. You look at the standard function on the 3 sphere, the real values, standard ice function, and you take a link in S3, and you look at your manifold with non-empty boundary is the S3 minus a tubular neighborhood of L. And your function is the restriction of H to this manifold. And as you know, in general, for closed manifolds, Morse theory says a lot on the topology of a manifold, and I hope that it is the same for this generalization. So I must specify what is a generic Morse function. Of course, it is. So I don't repeat that M. It is in any dimension. And the boundary of M is non-empty. And my function is Morse. That means the critical points of F are non-degenerate. And generic means the following, that the critical set is disjoint from the boundary. That means the differential of the function does not vanish on the boundary. Of course, you can look also at the restriction I denote by F del. By definition, the sorry? No critical points. That means sorry. Sure. This function, the restriction to the boundary, is also Morse. That is the definition for generic Morse function. And in that case, it is very well known that there are 2 types of critical points for this function on the boundary. Critical points of this function is decomposed as 2 types of critical points. is one union of type D. N is like Neumann, I explain later, and here is like Dirichlet. And what is the definition for this type of critical points? Neumann is this one. I make a picture in dimension 2. The manifold is here. The boundary is here. Here you have a critical point. Of course, the function is a Heiss function. And if you look at, here is a point P. If you look at the outgoing, the normal pointing outwards, you have this property, the differential of f at P evaluated on this vector is negative. That is the picture for Neumann. And the picture for Dirichlet is the opposite. Here, the normal pointing outwards gives a positive evaluation on the differential at P. There are the two types of critical points. And now I define modules like usual. Ckn, it depends on f. Ckn is just a Z module generated by the critical point of f in the interior and the critical point of index k and type n for the restricted function. This is a free module of finite type. And the second one it is not exactly the same. It's generated by the critical point of f and the critical point of type D and index k minus 1. I'm going to explain later this shift of the grading for the restriction. And now the theorem is the following. Maybe I theorem. First, C star n of f can be equipped with a differential, of course, of square vanishing, such that the homology of this complex, sorry, I'm speaking of n. The homology of this complex is isomorphic to the absolute homology of, I can specify the grading, the hk of this complex is isomorphic to hk of m with z coefficient. The second part is something analogous for the other complex of type Dirichlet, C star D of F, blah, 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 with a differential such that its homology is isomorphic to the relative homology of M relative to boundary. And there is some subtleties. The coefficients are Z twisted by the orientation, because the manifold is not assumed to be orientable. There is a third part that I am not describing. There is a short exact sequence, but it is not exactly as usual, because the Morse complex of the restriction to the boundary does not embed a subcomplex of any of them, but it is almost true. Anyway, there is a short exact sequence. And fourth part, all these complex have A infinity structures, not at all canonical, depending of a lot of choices. And if I am not an algebraist, and it is difficult for me to enter Fukaya's theory, but the language of Fukaya's allows one to avoid all the difficulties coming from the choices. So the good language is a category language, but I prefer the algebra language because it is easier for me, and there are n structure of algebras. I explain later. I have to say something. The first, this part is already published in I pronounce like it is Latin title, Geometriae Dedicata. That means devoted to geometry. And the last part is a work in progress with Christian Blanchet from Paris, who is a topologist in TQFT. So I would like to explain this theorem. First, I'm sorry, I'm going to explain a little bit the history. I need my paper for the dates. Brief history. First, for closed manifolds. As you know, Morse is not responsible for the Morse complex. He proved the Morse inequalities without using the Morse complex. If you have a Morse complex, it is obvious to get, it is an exercise of algebra to get the Morse inequalities. The Morse complex first appear in Smale, Steve Smale theorem on H-cobordism and generalized Poincaré conjecture, and it is published in the Annals 1961. You can find all the material for the Morse complex, except the name, of course. And he proved that he found that with a pseudo gradient vector field, this is satisfying what is called now Morse-Smale condition. That means transversality of stable and unstable manifolds. Then this one is a Morse complex. And next, you have Witten, the famous paper, Supersymmetry. And what? Morse theory? In Journal of Differential Geometry, 1982. And I would like to comment a little bit this approach by Witten. You look at the differential of the RAM, I denote like that, and you conjugate by the exponential of your Morse function. There is a sign. Here you put f over h, and here it is f over minus f over h, and in front you have h. And that is the differential of Witten. And you add a Riemannian metric, and you get Laplacian, Witten Laplacian. And it has the following properties. It has the following properties. If you look at the differential forms in any degree, differential forms which are eigenvector with small eigenvalues, these forms equipped with this differential generate generate a Morse complex. That means it is isomorphic to something generated by the critical points of the function. So if you look at this statement, I should mention something. The paper by Witten was a sort of program, and there is a lot of work in analysis, and it was done by worked out by Elfer, and Sjöstrand. But now there is something which is obvious. You can, instead of a closed manifold, you can take a manifold with boundary, and you can look at exactly the same program with boundary condition of type Neumann or of type Dirichlet, and it works. And it was done. It was done by people whose name for manifolds with non-empty boundary, same program, works. The first paper is due to Chung and Liu in 1995. And there are some additional assumptions here, and the final theorem is due to Helfer and Nier in 2006. And Francis Nier is is a mathematician in the University of Rennes, which is in Brittany, in France, and so it is close to me. And I discussed with him, and he asked me, it is strange, by the way of analysis, you can get a Morse complex, and what happens by the usual tool of topology. And in fact, it works. But, and I proved this. I am going to explain. And after that, I look at, I am not used to read many papers, so I am not informed. But having a statement, a theorem, I look at literature. And I found a lot of papers of the topological approach for Morse theory on manifolds with boundary. And it is very strange, because of course there is some difficulties, because if you like at the gradient, it is very complicated, because sometimes it is pointing in and sometimes it is pointing out, And it is very difficult to arrange all these things. And for instance, I look at a paper, and it is strange because he said in the end that it does not work for the annulus in the plane. And finally, I put this text on archive, and I received a message from Patrick Massot, who is known for people here, and he said me, look at the first chapter in Kronheimer-Mrowka book. It is about that. And it is very strange, because it is very complicated. And the reason why it is complicated is exactly that he considers a situation which is not generic. Because the assumption is that you can double the function. That means there are critical points on the boundary. And the formulas are very complicated. And if you look at the generic picture, it is very simple. It is coherent with an idea of Tom. If you look at the singular configuration, you get all the information you have in the neighborhood. If you look at a generic configuration, you have only one information. So I am going to explain this part, and the next talk I explain the second part.
I think the reason that it's very complicated in their book is because they want to extend it to infinite dimensions.
It is not the only reason, I think.
I mean, one of the reasons.
Maybe. Okay, right. So what you have to do, I explained first the first point. What you have to do, you have to create a differential. That means you have to construction of a pseudo gradient adapted to the boundary situation. And I start with an exercise. Preliminary question. Find a vector field such that you have the Lyapunov inequality x deriving f is negative out of crit f and crit f del, and x pointing inwards. Of course, it is a local problem. If you have local solutions of this question, you can combine all the solutions by a partition of unity, and you have a global solution. So you have your boundary, boundary of M. The manifold is here. you are at this point, and you have to satisfy two conditions. The first one, so the vector is pointing below, and the second one, the vector is pointing inwards. So you must be in this cone, more precisely in the interior of this cone. In general, you have room here. But there is an obstruction for this problem. It is exactly the points where the cone has an empty interior. And the cone has empty interior exactly at this point. So these points are obstruction to finding such vector fields. So I'll modify a little bit the condition. It's just my idea. So what is the definition of an adapted pseudo-gradient? Xn is an adapted pseudo-gradient if first the Lyapunov condition same. Next, this vector field is tangent to the boundary near the critical point of type Neumann. And x is pointing in the complement of these neighborhoods. And there are still another condition which already appeared in Smail's theory, which is a non-degeneracy condition at the critical points. With this condition, it is clear that x must to vanish at the critical points, but you specify that the vanishing is non-degenerate, and a way in doing that is you ask that x derived f, which is a function, is a Morse function. It is a generic condition on x if f is a Morse function. So I explained that with such a vector field, you have a differential, as usual, due to the following property. Observe that such, forgot it is still xn. this vector field, observe that this vector field is positively complete. That means you have a flow, complete flow in the future for positive time. It is impossible to go in the past because you get out the manifold. But in the future, maybe sometimes the orbit is tangent, but it is never going outside. So you have, as usual, unstable manifold of dimension k, most precisely diffeomorphic to Rk, if P is a critical point of index k of F, or a critical point of index k of F del. So you remember that the most complex consists in counting the connecting orbits. So you have to look at the stable manifold. But there are no stable manifolds. There are no stable manifolds because it is not possible to apply the flow in the past. But you can do it for a small time. Due to the tangency to the boundary, you have, I make a picture and explain that. I have this. The local model for, I make a picture in dimension 3. Here is the boundary of my manifold. Here is a critical point. And it is a critical point of type Neumann. That means the manifold is above the tangent plane at it. The manifold is in this region. Here is M. That is boundary of M. And there is a Morse model because you have all these non-degeneracy conditions. There is a Morse model for this picture. And there is a local stable manifold like that, and it is like that. Here is the index is 1. That is WS log of P. And it is diffeomorphic to dn minus k plus, that means half ball. One part goes in the boundary of manifold, and the other part is the interior contained in a level set. Contained in level set. So it is enough for having intersection of this global object with this local object, and you can make them Morse mail you ask Xn is Morse male, assume the generic condition Xn is Morse male, and you can count the connecting orbits with signs if you take some orientations. So you choose an orientation for the arbitrarily orientation for the unstable manifold. And so the stable local stable manifold are co-oriented. But it is exactly what you need for having counting of signs when you intersect something which is oriented with something which is co-oriented. You can count the signs. And you write down the usual formula. The differential of type n of a point, critical points of index k, evaluated on y, which is a critical point of index k minus 1, critical points in the interior or critical points of the restriction to the boundary. And it is the sum, the algebraic sum of lines in the intersection of W X W S Y lock. If you prefer, you intersect, you look at the trace on a level set of the function and you count the number of points with signs. And the proof that the square of this morphism is 0 is exactly the same as usual, because you have the same picture. The picture takes place in the interior of the manifold. There is no contribution of the boundary, because you see what happens on this picture. Here you have the stable manifold, and here you have the local unstable manifold, but after some time it is pointing in the manifold. And you prove very easily that it does not depend of any choice. And you calculate on example, and you look at the absolute. The homology is invariant by deformation of the function and the vector field. And if you look at a particular case, you find that you calculate the absolute homology. What about the second? Proof of 2. You have almost nothing to do. Of course, you look at the function minus f. And what about the function minus f? You have the following. The critical point in the interior of f are exactly the critical points of index n minus k of minus f. That's for the points in the interior. And the critical points of type Dirichlet and index k minus 1 of the restriction to the boundary are the critical points of index n minus k of minus f and type Neumann. If you remember, if you reverse your function, you pass from this picture to this one. So you have the exchange. And here I explain the shift because the sum of this index should be the dimension of the boundary, that is n minus 1. And that is the reason for this. And now what I am doing, set C, K, and D in subscript. It is not the complex I mentioned in 2. It is another one, the intermediate complex. And I'm sorry, of course, for having a differential, I need a vector field adapted. So you choose xd and adapted pseudo gradient for the function minus f. So that means it is tangent to the boundary near the critical point of type Dirichlet, and it is pointing in elsewhere, but it is adapted to minus f, so the Lyapunov inequality is reversed. And now you have a complex, but you have a cochain complex. I define first a cochain complex, and I first calculate the relative cohomology. The cochain complex is this. So the K is in superscript of F with a vector field xd, and by definition it is C star below, CK below, exponent Neumann of minus f and this vector field. And of course, it is a complex which is, it is a cochain complex because the differential, I'm sorry, n minus k. N minus k. It is a cochain complex because here the differential has degree minus 1. So due to the reversing of the grading, the differential has degree plus 1. It is a cochain complex. And by construction, this cochain complex, its cohomology HK of this cochain complex, blah, blah, is exactly the homology in degree n minus k of the chain complex of type n. And this one, by the first part of the theorem, is isomorphic to Hn minus k of m with z coefficient. So you have no choice. You have something which is calculating the homology, so by Poincaré duality, or Alexander duality if you prefer. I call that Poincaré duality. This one must be isomorphic to hk of m relative to boundary, but with twisted coefficient, twisted by the orientation. If you don't like twisted coefficients, assume that the manifold is oriented. But I want to have a chain complex. What I am doing, I take the transpose complex. I define Ck of type Dirichlet associated to F and this vector field as being hom of the previous one to Z. And now you open your favorite book in algebraic topology, and you look at something which is called the theorem of universal coefficient theorem in cohomology, and you calculate. You have to take into account torsion and to be a little bit careful. But due to the fact, the point is that this has finite type, since this complex is free finite type, finitely generated, sorry. Its homology is isomorphic to H star. And if you want to have the absolute, the relative homology with constant coefficients, you start with the complex C star of type D, tensor this local. And you can, this has meaning to take a homology of such a complex, and it gives rise to homology with Z coefficient. Now, there is something which is a little bit mysterious here in the transpose operation, because you would like that you have a geometric object for associated to the generator. And I would like to show you the picture, and I explain in the same time. Actually, I was a little bit lying in saying that there is no global stable manifolds for critical points. Actually, there exist global stable manifold. And what it is, you have a semi-flow defined in the future. And you look at the point, at all the points whose positive orbit enters the local stable manifold. That is the union for all the time, positive time of the flow, of the pre-image that is not F minus T. It is a pre-image by phi t of WS log of X. And that is a geometrical object associated to the generators of this complex. And I would like to show how it looks like. Here you take the standard unknot in S3, tubular neighborhood, and you have 4 critical points. At each time you have a critical point on the knot, you have a pair of critical points on the boundary. But in this pair, one is of type Neumann, the other is of type Dirichlet. Okay? And I am interested in the complex generated by the Dirichlet critical points. And you have 2 X, which counts with degree D, with the degree 2, because it has index 1 on the boundary, and you have to translate by 1. So it is in degree 2, and this one is in degree 1. And you have also the maximum of the height function and the minimum of the height function. In total, you have your complex is generated by 4 critical points. And I am interested, the vector field you are looking at is going up because it satisfies the Lyapunov inequality for minus f. So it is in the increasing direction. And for good choice, the picture is like that. It is finally the global manifold, stable manifold of X is a disk whose boundary is in the boundary of your manifold. Okay? For this choice of a vector xd pointing, you see here it is a critical point of type Neumann. So there is no tangency condition here. It is pointing in. It is tangent near x and near y. And in red, there is a global stable manifold of X, and in blue, the global unstable manifold of Y, which has index 1. And this line, in fact, a short piece of this line is a local stable manifold of Y, because it has index 0 on the boundary. You translate by 1, it has degree 1. And there is one line coming from the minimum and ending in Y. And there it is one picture. But you can choose a different picture, a different vector field. And I would like to show the other one. You can create, it is more complicated. You can create connecting orbit from Y to X. In the previous pictures, there was no, the manifold were disjoint. Here you have a pair of connecting orbit. And of course, if you have a pair of connecting orbit, if you, by pushing the finger, you create this pair of connecting orbit, it modifies the global stable manifold of X. And it is a picture like that. What it is still a disk. It is not possible to make more. Here it is very clear, and here it is a little bit. So maybe the best is to repeat this picture. I look at WS of X and its compactification. And in the closure of this manifold, you have this line counting twice. And if you cut along this line, you get such a picture. That means picture like that. And here you are in the boundary of M. Here is X. And this line has the same image. You glue together both lines, and it is the point Y. And your vector field is tangent. It is a red vector field. It is XD. Here you have the local stable manifold of X, tangent, tangent, and pointing to X. Here it is pointing in, 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 and here it is a source. So it is coherent. There is no problem of index. And I think that in general it is not very complicated. More or less it is typical of the complexity of this object. And looking at these pictures, for the Borromean link, I am able to prove that it is a non-trivial link using Morse theory. And I explain that with infinity structures next time. Thanks a lot.